Albert Einstein. Relativity, the special and the general theory. Have you ever looked up at the night sky and felt a sense of wonder, pondering the vastness of the universe and our tiny place within it? Perhaps you've questioned how time works, or why everything exists the way it does. If so, you're not alone. These are questions that have intrigued humanity for centuries, pushing the boundaries of our understanding and challenging our very perceptions of reality. But what if I told you that the answers to some of these questions lie within the realm of one man's mind, and a theory that has revolutionized the way we view our universe? In this blink, you'll embark on a journey into the core of Albert Einstein's groundbreaking insights into relativity, space-time, and the fabric of existence itself. By delving deep into the intricacies of the cosmos, you will not only gain a deeper appreciation for the universe around you, but will also enhance your ability to think critically, challenge conventions, and understand complex phenomena. As we unravel Einstein's universe, you'll find that the world around you is far more fascinating and mysterious than you ever imagined. All right, let's begin. Understanding the speed of light. In the late 1800s, scientists were puzzled. Using special tools, American physicists Albert A. Michelson and Edward W. Morley measured light's speed in different directions as Earth moved. Their results? Light always travelled at the same speed, no matter how Earth moved. But how could this be, you might be asking? It's like driving a car and turning on the headlights. You'd think the light would move faster if the car was speeding, right? Well, it turns out this isn't the case. Here's where Einstein's genius shines. Instead of assuming there was an error in the Michelson-Morley experiment, he suggested a groundbreaking idea. The speed of light remains constant for all observers no matter their relative motion. In essence, light doesn't follow our common sense based on everyday experiences. It has its own set of rules. Now, you might be wondering, how does this idea of constant light speed play out in real-world scenarios? To see how this works, imagine two friends, Alice and Bob. Alice is on a train station platform and Bob is in a fast-moving bullet train. Both of them have stopwatches. When the train speeds past Alice, they both start their stopwatches at the exact same instant. Here's where things get strange. If Alice could magically look into the train and see Bob's stopwatch, she'd notice that it seems to be ticking more slowly compared to hers. It's not that her eyes are deceiving her, or that there's some trick of the light. It's a genuine difference in the passage of time. This weird phenomenon is because of something called time dilation, which is predicted by Albert Einstein's theory of relativity. According to this theory, as objects like the bullet train move really fast, close to the speed of light, time for them seems to slow compared to objects that are stationary or moving more slowly. So from Alice's viewpoint on the platform, Bob's time on the moving train is actually going slower. However, from Bob's perspective inside the train, everything feels normal. It's as if he's not moving at all and time is ticking away as usual. But if he looked out and could see Alice's stopwatch, he'd think hers was running faster. For centuries, we clung to the Newtonian notion that time is absolute, ticking away the same for everyone, everywhere. Yet Einstein challenged this foundational idea by figuring out that the faster something moves, the slower its time appears to pass compared to something that's not moving as fast. He called this spacetime, a fusion of space and time. In Einstein's universe, time could stretch and squeeze, affected by one's relative motion. The consequences of this revelation were profound. For example, if you were to journey into space at near light speeds and then return to Earth, you might find that less time has passed for you than for those you left behind. But here's where things get even stranger. Let's return to Bob and Alice. From Alice's point of view, as Bob's train speeds past, it isn't just time that's affected. The train itself appears contracted, squished in its direction of motion. It's shorter than when it's at rest. And once again, this isn't an optical illusion, it's one of the bizarre yet fundamental truths of our universe. As we venture further into Einstein's universe, remember this: what might at first seem impossible or absurd can, with a shift in perspective, unveil the underlying fabric of reality. In the next couple of blinks, we'll peel back the layers of Einstein's revelations and we'll see that space, time, and the very nature of reality aren't quite what we once believed them to be. Let's continue. The fine line between gravity and acceleration. Imagine you're inside a sealed elevator with no windows. You feel a force pulling you downwards. There could be two main reasons for this sensation. First, it could be gravity. This is what you experience every day on Earth. The planet's gravitational pull is drawing you towards its centre. Secondly, imagine the elevator isn't on Earth but floating in deep space where there's no gravity. However, a spaceship is towing it, accelerating it upwards at a specific rate. This acceleration creates a force inside the elevator that mimics the feeling of gravity. This is where another of Einstein's key insights lies. He proposed that one can't tell the difference between the two elevator scenarios. Whether it's the gravitational pull of a massive object like Earth or the acceleration from the spaceship, the effect feels the same to you. That's why Einstein proposed that gravity and acceleration are indistinguishable from one another. It's not about what's real, but how forces and motion are experienced from a certain perspective. Yet here's where it gets even more interesting. If gravity and acceleration are equivalent, then maybe, just maybe, gravity isn't a force at all. Maybe it's something far more profound. Take this example. Have you ever noticed how water swirls around a drain, spiralling inward? Now think of space-time, the fabric of the universe, behaving in a similar way around massive objects like planets and stars. Instead of objects pulling on each other through some invisible force, Einstein saw it as celestial bodies creating a sort of spiral or dip in space-time, much like water around a drain. So when you feel like Earth is pulling you, it's actually because you're moving along the curved path in space-time that Earth creates. This shift from Newton's gravitational force to Einstein's space-time geometry was monumental. It wasn't just a change in the technicalities, it was a whole new way to view the universe. Now, it might be, by this point, that you're feeling a little bit skeptical. Sure, it's a beautiful theory, but does it hold water? Einstein thought so, and he made bold predictions. One of the most striking was about Mercury. For the longest time, astronomers were baffled by Mercury's orbit around the Sun. It exhibited a peculiar shift, a precession that Newton's laws couldn't explain. Yet, through the lens of general relativity, this mystery unravelled seamlessly. Einstein's predictions matched Mercury's odd behaviour to a T. Think back to the merry-go-rounds you probably enjoyed in your childhood. Imagine you're watching one and you notice that one of the seats has a weird, unpredictable wobble every time it goes around. That's a bit like what was happening with Mercury. As it went around the Sun, it didn't move as expected. There was this tiny twist in its path, a sort of extra wiggle that couldn't be explained using the then-accepted Newtonian laws of motion. People were stumped. But that's where Einstein's idea comes in. Maybe space itself is curved around massive objects like the Sun. When you use this idea, Mercury's weird movement makes perfect sense. As we dive deeper into Einstein's universe, it's evident that our prior understanding was just the tip of the iceberg. We live in a universe where space and time meld together, where gravity isn't a force but a curvature, and where our very notions of reality were wrong all along. So with this new understanding in hand, let's now move on to how Einstein revolutionized our perception of the cosmos. The curvature of the universe. Imagine growing up being taught that the Earth is flat. You've always been certain that you're walking on a vast, never-ending plane, but then one day someone tells you the Earth is not flat, but round. Your entire perspective changes. This is similar to the revolution Einstein brought about with his notion of non-Euclidean geometry. Unlike the flat, plane geometry we learn in school, Einstein presented a universe that's curved and warped. This is essential for understanding relativity and how we fit into the vastness of the universe. To understand this better, think of an airplane journey. Imagine you're at the North Pole. You hop on a plane and fly straight down to the equator. When you reach the equator, you make a sharp right turn and travel a quarter of the way around the Earth. You make another sharp right and head back toward the North Pole. Even though you've made these turns, you find yourself back where you started. This might seem odd, but this route you've taken is the shortest possible path on the curved surface of our Earth. This strange path is what Einstein termed a geodesic, or the shortest path in a curved space. It's different from what we're used to in flat spaces, like a flat map of the world. Einstein showed that this concept equally applies in the universe at large. Sure, when we look up at the sky, space doesn't seem to have any visible curves like the Earth does, but Einstein proposed a radical idea. Space isn't flat. Just like our Earth has curves and valleys, space itself can be bent and curved. And what causes these curves in space? Big, heavy objects like planets, stars, and galaxies. So when objects move through space, they're not just flying aimlessly, they're like our airplane, taking the shortest path through these invisible curves in space. Think of it like a marble rolling down a bowl, following the curve toward the bottom. In space, objects roll along the curves created by big, heavy things, always taking the shortest path, or the geodesic. Now, why is all this talk about geometry, space, and time essential? Because the shape and structure of the universe are directly influenced by its contents. The stars, galaxies, and planets all dictate the curvature of our universe. Let's move on to our next section, where we see that Einstein didn't just stop at redefining our understanding of time and space. He ventured into the cosmos, discussing its fate and structure. Einstein's cosmic philosophy. Have you ever gazed up at the night sky and pondered our place within the vast cosmos? It's a natural human inclination, after all. Einstein took this curiosity and expanded our understanding of the universe in ways that might seem both bizarre and fascinating at the same time. For example, in Einstein's view, our universe is not infinite in the traditional sense. Picture, if you will, a globe. Now, you can keep travelling in any direction on its surface and never find an edge, right? Similarly, our universe might be finite, but without any boundaries. It's a concept that's tricky to visualize. You might wonder, how can something be finite and yet boundless? Yet this is the marvel that relativity brings to the table. It challenges our preconceived notions and urges us to think beyond our everyday experiences. Building on that, consider how the vast celestial bodies, those very stars and planets we marvel at, influence this boundless universe's shape and form. Think back to how these massive objects warp the fabric of space-time. Now let's scale this up. The collective matter in the universe decides the overall curvature of space-time on a cosmic scale, and this has some pretty significant implications. Depending on the density of matter, the universe can have different shapes and fates. For example, if the universe has a certain critical density, it would be flat, akin to a bedsheet being held tightly at the corners. If the sheet is perfectly stretched without any sagging, then it has the right amount of matter in it. Now, what if we placed a heavy ball in the middle of that sheet? The sheet would sag around the ball, right? That's like a universe with too much stuff in it, causing it to curve in on itself. On the other hand, if there's too little matter in the universe, it's not like a flat sheet or a sagging one. Instead, think of it as a Pringle chip or a saddle where the edges rise up and the centre dips down. That's how the universe might look if it's lacking in matter. These shapes aren't just mathematical curiosities. They dictate the destiny of our universe. Will it keep expanding forever, eventually collapse, or find some equilibrium? Einstein thought about these destinies deeply, and while the complete answer remains elusive, his framework paved the way for our modern understanding. Beyond the technicalities, Einstein often dabbled in the philosophical ramifications of his theory. What does relativity say about our reality? Are space and time absolute entities, or do they mould and change based on one's perspective? These musings often veered toward determinism, the idea that all events are determined completely by previously existing causes. If anything in the universe operates based on set laws, is there room for randomness? Or is the universe a vast, deterministic machine? Furthermore, Einstein reflected upon the essence of scientific theories. To him, they were more than mere equations. They were attempts to grasp the underlying order of the universe. They bridged the divide between the observer and the observed, intertwining subjectivity and objectivity. Einstein invites us to view the universe and our place in it through a radically different lens. A lens that might seem abstract at first, but that ultimately paints a richer, more intricate picture of how reality works. The next time you look up at the night sky, remember, it's not just about stars and galaxies, but a magnificent pantheon of space-time, matter, and the very nature of existence. In this blink to Relativity by Albert Einstein, you've learned that late 19th century experiments led to Einstein's groundbreaking conclusion: the speed of light is constant for all observers. This revelation introduced time dilation, in which time can appear to move slower for fast-moving objects. Einstein's theory of relativity described space-time, a blend of space and time affected by motion, challenging Newton's idea of absolute time. The theory also illustrated that gravity isn't merely a force, but a curvature in space-time caused by massive objects. Einstein's general relativity solved mysteries like Mercury's orbit, reshaping our understanding of cosmic movements as they roll along space-time curves. Einstein also proposed a boundless yet finite universe, its shape dictated by its matter content. This shape ultimately hints at the universe's fate: eternal expansion, collapse, or equilibrium. Beyond the science, Einstein pondered the philosophical implications of his work, musing on determinism, the nature of scientific theories, and our profound connection with the universe. Thank you so much for listening. Please leave us a rating or a comment. We always appreciate your feedback. And we'll see you in the next blink.